If you take a piece of material and you make it smaller and smaller, or you modify the microstructure, going to the scale of a few nanometers, properties are changing, and we are using that to develop new applications. This is a so-called Eureka Cluster. This is a new major program to revitalize metallurgy, in particular in Europe. This is a program that has been initiated by the European Space Agency, and we are in the stage to build an office, the headquarters of that program, here at Ulm, and this should be continuing for the next 7 years or something like that. And we plan to have a funding situation of several hundred million euro. Well, there are plenty of new developments using composites, for example, for a number of applications. What we are interested in particular, nanocrystalline materials, nanostructured materials, and also bulk metallic glass and coatings, functional coatings, hard coatings, for example.
Many metallic alloys in the liquid phase are highly reactive. That is, when you contain these alloys in some measurement device, they tend to react with their container, and this makes measurements very difficult, and the results are often fraught with error. The solution is containerless processing, and for containerless processing you can use electromagnetic levitation, and we have developed methods for the containerless measurement of thermophysical properties. Electromagnetic levitation is a process by which an electrically conducting material is exposed to a high frequency electromagnetic field, and this power is absorbed, creates heat in the sample and creates currents, and through the interaction of these currents with the outside electromagnetic field, it is possible to levitate or to position a metallic sample without contact to its environment. The application is primarily modeling of casting and solidification processes, and a more general material physics application is better understanding of thermophysical properties in the liquid phase. We have done many experiments in the past on board parabolic flights with samples from various industrial partners. We have also now a set of experiments on the International Space Station, that is the electromagnetic levitator in the Material Science Laboratory on board the ISS, and there we have an extensive series of measurements of thermophysical properties of industrial alloys, of bulk metallic glass forming alloys, of generic composition, which are important, for example, for the steel industries. So this environment allows us extensive investigations of thermophysical properties of liquid metallic alloys.
It's well known that diamond is the hardest materials of all materials. But next to that, diamond has got the highest Young's modulus. That means that diamond is a fantastic material for mechanical applications. Diamond is a wide bandgap material with a bandgap of more than 5 electron volts. That means diamond is an electrical isolator. In the last few years, our group has developed a new process to increase the conductivity. That means our material now has got semiconducting properties. Our nanodiamond now can use for applications in the area of microelectromechanical systems. We have started to develop actors and sensors. As an example, we've developed a prototype of a piezoresistive pressure sensor made of nanodiamond, which is suitable for harsh environments. Diamond can be microstructured using similar methods known from silicon technology. With these techniques, we have developed microparts for mechanical watches out of freestanding ultra-thick nanodiamond layers. In order to reduce the production cost, instead of using thick diamond films, we are using structured silicon microparts with a 3-dimensional nanodiamond coating. The big advantage of using nanodiamond microparts for mechanical watches are their low friction coefficient and the possibility of running mechanical watches in an unlubricated state with a high accuracy. I believe that nanodiamond will be used for more and more applications where its superior material properties can be utilized. Particularly, the possibility of conductive nanodiamond will lead to many interesting applications in the field of micro electromechanical systems. Diamond is not only a girl's best friend, nanodiamond can also be a material scientist's best friend.
Microtechnology has become more specialized, going to smaller and smaller dimensions into the range of a few nanometers, and actually we are in the stage of editing a book that should be published in January next year, that is showing, as a second edition actually, that is showing how effects of nanotechnology can be transferred to actual commercial systems, components, sensors, for example, in microelectronics, in the field of medicine, in energy. Energy storage is an important issue, transport and others.